Hey guys, it's Landon with RH and Taught by a Surveyor. This is the second video that I'm recording about survey error management and errors in surveys and survey measurements. So if you haven't watched the first video, I encourage you to go do that. It talks about the four sources of error and PAG, precision, accuracy, and granularity. So in this video, we're not going to do any math. We didn't do any math in the first video. We're not doing any math in this video, and you're going to notice as you move through this series of videos that I don't do any math for the first few videos, and that's because one, you need to understand the concepts, and two, like people introduce fancy math into this process way too early, and I don't want to do that. We're not doing any fancy math, but we're not even going to introduce math for a little while. So no math in this video, so don't panic. Okay, so we're going to talk a little bit about the different types of problems we get in our data. So, if you've heard the Ariana Grande song, 99 Problems, but you ain't one. So we're talking about 99 problems. And then I'm going to go over some rules for errors, and then we'll talk a little bit about the bell curve. I'll just give you a gentle introduction to the bell curve. Don't fall asleep or switch to a shuffle video. It's going to be okay. The bell curve is not going to kill you. It's not going to bite you. All right. So there's really three types of problems that we worry about in our measurements as land surveyors. The first two we call errors. So there's two kinds of errors, and then we have blunders. Okay, so I'm going to lean up against my chair there while I talk about that like an old professor. Okay, so the two types of errors we have are random errors and systematic errors. Okay, so random errors are just errors that occur because of all the randomness in the universe and the small imperfections in the world that we operate in our equipment, and in our eyes, and in our hands, and in the atmosphere. So that's why we call them random. Some of that type of error is just caused by the randomness of the universe that we are living in. And so I'm going to come back and talk about in a minute how do you tell the difference between random and systematic. So just remember, random errors are caused by the universe that we live in, and they tend to not follow a pattern. Okay, systematic errors do follow a pattern, and they're usually because there's something wrong in the system that we're using to make our measurements, right? That's why they're called systematic errors. So how do you tell the difference between random errors and systematic errors, and why is that important? So random errors, and you can read this, it's in your survey textbook. So random errors tend to be small compared to the other two types. They tend to be small. Now that's relative, right? Small to one person is big to another person, but they tend to be small when compared to the other types of errors or blunders. They tend to cancel each other out, and they don't follow a pattern. So when I say they tend to cancel each other out, what does that mean? That means if you read, so that means that the technical way to say that is the random errors tend to be opposite signs. So some are positive, some are negative. And you'll see that when we get into a little bit of the math. But let me try and explain that in a non-mathy way. Okay, what that means is if the error is random, it's just as likely to be a positive number as it is a negative number. So if you're reading a Philly rod and the error is random, you're just as likely to read the rod a little bit high as you are to read the rod a little bit low. What that means is over a long series of measurements, the random errors tend to cancel each other out. In other words, they tend not to accumulate. You don't have a big negative error or a big positive error when you sum up your random errors because they tend to cancel. And we'll learn a little bit more about that when we get into the probability behind the bell curve. We're not going to do that in this video, but probability teaches us a little bit about that. Okay, systematic errors do tend to accumulate, and they do follow a pattern. So a systematic error is if you've got let's say so this has actually happened to me. you've got a field crew, they go out with a Philly rod and they forget to put in the bottom piece. So they're missing the bottom 6 feet of the Philly rod. Yeah, that's going to be a systematic error, right? You're going to see that in all the measurements. Or you've got a total station that's been improperly calibrated, and so all the EDM measurements are off by either the same amount, fixed amount, like 2/10 of a foot, or like if you got the wrong prism constant, or there's an error that scales. So it's always 2% long or 2% short. Don't let me forget, guys. I need to do a video where I talk about errors that scale versus errors that are fixed. That'll be important for later. Okay, so normally systematic errors we can identify because they accumulate. So the more you measure, the bigger they get, and they follow a pattern. They tend to not cancel each other. So they tend to be the same sign, positive, all positive, or all negative. Okay, then the last thing we have is blunders. Blunders is just when something really bad goes wrong. And normally the source of blunders are human error. But, so, you know, it's you're the surveyor and you cite the wrong prism. You got more than one backside up, or you got more than one rod up, and you cite the wrong one. That's a blunder. But blunders they're almost always human caused, but not always. Another example of a human error is you write down the wrong rod reading in your field book. But they could be other things. So for example, a tripod could settle way out of plumb. And if you're doing static work, you don't notice that when you pick it up. That's an example of a blunder, probably. So blunders are big. They can be very hard to find. So blunders, so there's a couple reasons why we repeat measurements as surveyors, and you're going to see as we work through this series of videos, good surveyors are always repeating measurements. And the reason why is it allows us to do two important things. One is it allows us to model our random errors, or estimate our random errors. In other words, estimate our precision. And the second reason is repeated measurements help us find blunders. And that's going to be really important when we talk about how error management works in static GPS networks. That's why we double occupy points in static GPS networks. So blunders are hard to find. That's why we repeat measurements. One of the reasons why, because it helps us to detect blunders. That doesn't mean we're always repeating measurements, but critical measurements we typically repeat because we want to detect blunders. Okay, so let me switch gears here. We're going to come over to this other whiteboard, and we're going to talk about, it's important to understand the differences between these three types of problems here. Right? Okay. Try and get the Ariana Grande song out of your head for a minute. You want to be able to tell the difference between these types of problems here, because as surveyors, we do different things to deal with the problem. So I've got 3 rules here. These are just basic rules for how we deal with these 3 kinds of problems, okay? So rule number 1, for random errors, we try to the extent possible with our measurement techniques to reduce those, and then whatever we can't reduce, whatever's left, random errors left, we adjust. So the little bit of random error that doesn't cancel, that's left over, we adjust that out. Whoop, sorry, there goes my T. Okay, rule 2 for systematic errors, you don't want to adjust those errors. You want to find them and fix them if possible. So you want to find those and fix them. Okay, and part of how we do that is just by following good procedure. This is part of why good procedures are important. Okay, and then the last rule number 3 for blunders, we also want to find and fix blunders, and then sometimes blunders can't be fixed, which means you might just have to eliminate some data. Okay, usually with systematic errors, we can make a correction to the data. We don't have to throw it out. Okay, but a lot of times with blunders, you can't fix it. You just have to eliminate it. You have to eliminate the data. So in red there, I've got a couple kind of footnotes, side notes. So for random errors, when we go to adjust, there's different ways we can do that. So you can pick your method, and the methods have trade-offs. Different methods there's pros and cons. So part of what we'll talk about in this video series is the different methods you can use, and some methods you can use with certain types of surveys, but not on other types. And they have advantages and disadvantages, so we'll talk about that. And then for the rule 2 and rule 3, when you have systematic errors or blunders, you might have to remeasure. So normally we don't have to remeasure because of random errors, but if you have a systematic error or a blunder, you might have to remeasure. You might not have to remeasure with systematic errors. If we can isolate that and determine the cause, we can normally fix it. But with blunders, you frequently just have to go out and throw some data away, and you got to go out and remeasure. Okay, so I want to talk about the bell curve. Just a gentle introduction to the bell curve. And you'll learn this in a probability class or a statistics class, and forgive me, my bell curve isn't going to be perfect. That's the basic shape of the bell curve. So this is what they call a distribution in statistics. It's a distribution of the error distribution. Okay, so it's one type, and it's the type that we most frequently see as land surveyors. Okay, so what does this mean? This shape that I've drawn. Okay, so you can think about it this way. This middle line right here, this is called the central axis. For our intents and purposes, we can call that the true answer that we're looking for, whether it's a distance or an angle or some other measured value. That's the true value. Okay, now remember I told you we don't ever really know what that is. We just estimate it. But let's pretend we have special surveying powers and we can determine exactly what the true answer is. So that's the black line. Okay, now the blue line is what you get when you draw a smooth line through all the actual measurements that we've taken. Okay, so it's actually when you take the measurement and you subtract it from the true value, you get either a positive or a negative number. We call those residuals, and we're gonna do some examples of this so you can see it. But when you plot those residuals, those individual residuals, if you take enough measurements, if you have enough residuals and you don't have systematic errors or blunders, you will find as you plot these, they always form this shape. A bell curve. It's a naturally occurring error distribution. And it doesn't matter if you're measuring an angle or a distance or an area, right? All kinds of different survey measurements. If you repeat those measurements over and over and then calculate the residuals based on the true value and you plot the residuals, so these will be negative residuals and these will be positive, negative residuals, positive, that looks like an X, sorry. Negative residuals on this side of the line, positive on that side. If you plot and the values get bigger as you go up, as you move right and left. Time and time again, as you plot those residuals, you get this same curve over and over. It's really kind of amazing. Like if you're a geek like me, you kind of geek out on that a little bit. It's like this beautiful pattern in math. It's like a mathematical footprint of the universe. It just kind of blows my mind, right? Over and over again, as you make repeated measurements, the random errors form this special kind of curve called the bell curve or the probability distribution, it's called sometimes. Okay, now, if you think about what we learned without any math, if you think about what we learned about random errors, you can see that the bell curve fits what I told you about random errors. So, large errors on these ends are less likely than small errors. That's why the curve is taller in the middle. Okay, and the curve is roughly symmetrical, which means if you add up all the positive errors and you add up all the negative errors, you're going to get close to zero. The errors cancel. Remember, I told you that about random errors. Okay, so that's the bell curve, right? And the reason the bell curve is important is because if we plot our residuals and we get a shape that looks like this, that tells us that we're dealing with mostly random error. So let me just tell you, for example, if we had a systematic error in our measurement, we wouldn't get a bell curve, more than likely. We might get a curve that looked like this. Right? That's not a bell curve. That tells us something else is going on. Now, in practice, we don't actually plot the residuals like this to determine what type of errors we have, but you could. Yeah, like this is a tool you could use, right? So most of the time, we know if we've got systematic error or blunders because we've repeated our measurements and we've done some other analysis like a closure analysis, like a loop closure or a geometrical closure. And so we know all we have left is random error. And then once we know we have random error, we assume we've got a nice bell curve, then we can use some different rules to adjust that random error based on what we know about the bell curve. Now, one of the reasons I'm teaching you about the bell curve, besides that you need to understand it, it's an important concept from probability that surveyors use. And I'll try and remember to do a video that talks about Pascal's triangle and the bell curve. But one of the reasons I'm teaching you about the bell curve is because the standard way we report the precision, not the accuracy, but the precision of our measurements in surveying is based on the bell curve. So we talk about how much of our measurements fall under a certain area of the curve. Is it 68% or 96% or 98%? Those are called standard deviations, if you've heard those. So the bell curve is important. I'm going to do a whole video just about the bell curve and standard deviation and how we report measurement precision. Now, I don't necessarily love that. I think there's also alternative ways you can do that, but that's the standard way, so I'm going to teach it to you. And I don't even know that we're going to do any math for that. We might do a little, just basic arithmetic, but I'll show you how that works, and maybe we'll even jump into Excel, and I'll show you how, if you have a set of measurements, how you can calculate the accuracy at 68% or 98% or so 95% or 99%. So we'll show you that because it's a standard thing that surveyors need to do, and I'll teach it to you, but it's based on the bell curve. It's based on, how many measurements are under 99% or 95% or 68% of the bell curve when you look at your set of measurement residuals. Okay. Now, one last thing, just to add, we never know what the true answer is. We can only estimate it, and so when we take, it's usually an average, but it could be a best fit value. When we take that estimated true value and we subtract it from all the other measurements, what we get left over we call residuals. And those residuals we assume are the errors. We don't really know if they're the errors because we don't know the true value. So we use an average or a best fit to approximate the true value, and then we use the residuals for each individual measurement that we calculate with that estimated true value. We use those, we substitute those for the actual errors. Remember, we never know the true value and we never know the true errors because we don't really have super surveyor X-ray vision superpowers, basically, is why. So, all right, I know this is a lot. This is deep, but it's really important, and I'm trying to make it as simple as I can. If you need to, watch the video again. And if you have questions, you can text me. My cell phone is all over the internet. You can email me, sunburn.surveyor@gmail.com or landon.blake@redefinedhorizons.com. Reach out to me. Give me a call. I promise I will try and get back to you. You might take me a few days, but I'll get back to you, and I can help you with this. And we'll do some more videos.